All right. Good afternoon, everyone. It is a great pleasure to be here. And even I cannot see you, it is a great relief to know that my colleagues are well and healthy. And it's been a tough year, but here we are still doing our best under the circumstances. First of all, thanks for giving me the opportunity to talk about our research. Since the general annual meetings allow you only present for 2 minutes, I believe this kind of rather small but intimate meetings are the best to get feedback from what you are working on. So today I will be talking about our recently published paper with the title Reconstruction Origins Without Biostratigraphy, the Saharides and Continental Growth During the Final Assembly of Gondwanaland. In this paper, we reintroduced and improved the term Saharides, which basically describes the Pan-African events in North Africa and in the Arabian Shield. So as I can see from the audience and knowing from my colleagues, I may say many of you worked or still working on the safe era of tectonics, where the geological record has not been completely erased. In this era, the kinematic reconstructions are relatively easy because you can get information from GPS, from marine magnetic anomalies, and by using the fracture zone orientations, pretty accurate reconstruction of large plates can be accomplished. And this is what we call global plate circuit. But when you go back in geological time, things get fuzzier. First, you lose insight from ocean floor. And if you go further and step into the Precambrian, you also lose the method of biostratigraphy, which means the ability to correlate different layer rocks in different areas. This is a huge problem for ancient orogenic belts because most of them experience multiple phases of deformation, plus erosion, that destroy their geological record, or as usual, they are covered by younger strata. So I will briefly talk about the method we use in order to handle this issue, but first, our area of interest. Not working. Oh yeah. So here you see a map of Africa showing it old pieces, I mean the Cratonic regions. So before I dig into the details of the region, it may be better to clarify some of the terminology that you already see on this map, such as craton, metacritone, and shield. So the name kratogen, or as we use today, craton, derives from two ancient Greek words. Kratos, one of them is a kratos, meaning might, strength, and the second one is genesis, meaning origin and creation. So the exact translation of a craton would be born strong. And cratons are composed of shields and platforms. A shield refers to the crystalline rocks of Precambrian age that are exposed in the cratons, and a platform, which is not present on this map, but you can see the best example in Europe, and it's called the East European platform. And it represents regions where these crystalline basement rocks are covered by horizontal or gently tilted sediments. So the red ellipse shows our study area. So if you are somehow interested or looking for related literature, I have to say you need to search with different names. And here I listed the popular ones from the literature. And the most popular ones among these are the East Saharan Craton and Sahara Metacritone these days. But if you ask my favorite, I would say the Ghost Craton. So it's kind of spooky. So as I mentioned, a new term is introduced and it's called Metacritone. So what is a Metacritone? As it is defined by Abdussalam et al. 2002, a metacritone is a craton that has been remobilized during an orogenic event, but is still recognizable dominantly through its rheological, geochronological, and isotopic characteristics. And here comes our first problem. A craton, as I mentioned earlier, as its name implies, is only defined by its strength and resistance to deformation. Of course, they have common characteristics and rheological properties, but neither its age nor its isotopic composition can tell whether a piece of rock is cratonic or not. It is like treating every Archean rock on planet as a craton, which is absurd. So on the right side, you see a map from the Lujoy et al. 2013, and you can see several small cratonic pieces that are scattered in North Africa. We were highly curious about its nature and evolution of the region because when you read the literature, you see every cratonic piece has several exotic terrains, island arcs that amalgamated in separate orogenic phases. Unfortunately, such models have some inconsistencies. For example, the inferred island arcs are impossibly smaller than the present-day arcs. So if you think North Africa is huge enough, let me show you a real deal. Here you see a comparison between Arabian Shield and West Pacific. So it is clear that a single Japanese islands or Marianas can take up much of the volume of the Arabian Shield. And additionally, assumed collisional sutures between those terrains are lack of accompanying structures that we see in present-day collisional systems, such as shortening-related metamorphic cores, elevated topography, etc. So first, we wanted to free ourselves from the terrain methodology and try to identify first-order units of an orogenic architecture, or as we called in this paper, essential units. So these are the basic elements in an orogenic setting, such as magmatic arc, fore-arc, back-arc basins, accretionary complex, fold and thrust belt, even the molasse basins. They don't have to develop properly in every orogenic belt, but they exist. And then we search for the secondary or accidental units, and these are formed by the ongoing deformation during the orogeny by dismembering the essential units, such as fore-arc slivers, block uplifts, and subsidences. So defining both of these units ideally requires well-mapped orogenic regions. It was our biggest challenge in here in Sahara. In the region we are interested because it's the desert. Most of the Precambrian rocks are covered by younger sediments, and published maps are quite old, and the ages of the magmatics and even the sedimentary rocks were not reliable enough. So this is especially valid for Sudan, Ethiopia, Nigeria, Chad, and partially for Algiers. And here you can see the distribution of the Pan-African rocks in here and on the map on the left side by the yellow color. So, and being lack of the index fossil for Precambrian is just making it worse for this time. So the first step in our approach to the Saharide was to identify the tectonic environments. This was relatively easy in Saudi Arabia, in Egypt, as you can see on the right-hand side, because they have beautiful high-quality maps that we could access. So our logic was to try to find traces of equivalents of the present-day environments. For example, when we see train of calc-alkalic, mafic to felsic intrusives, and volcanics, we first label them as products of magmatic arc. But we all know that magmatic arcs don't exist in isolation, so we also search for fore-arc and back-arc bodies. So this identification is the key to the tectonic map showing present-day distribution of the Pan-African tectonic environments. In this map, we plotted them onto a reconstructed map of Africa that we generated by G-plate software. This way, we could close the Red Sea. Here you see it's missing. And we could get rid of some of the internal deformation of Phanerozoic. Here you can see the polygons are overlapping. So actually this map shows more than you can see. So we need to zoom in to see the details. That's why we had to give this figure as a supplementary file because it's huge. The beauty of this map, it has multiple layers. So the first layer is trend lines. These are the guidelines to follow average tectonic trend in a region. This method is highly useful in absence of any other markers, such as ophiolites or in areas that are covered or eroded, as we see in the Saharides. In this map, red lines, here you can see them, correspond to the trend lines. They may not seem as lines, so let's zoom in a little bit. This is the area that I want to show you, and this is the detail that we worked. They represent the structural trend obtained from geological maps and satellite images. So the advantage of working in the areas of desert or in the arid areas, it's no vegetation. So here you see a list of structures that can be used to identify the trend lines. It can be either strike of a bedding plane, fold axial plane, a fault plane, or strike of foliation, sometimes strike of a trend of a hinge line, or the trend of morphological units such as valleys and summits. So you also see, I want to show the map again. blue lines in this map, and they represent our second layer, magnetic lineations. So we gathered and summarized available magnetic data from our study area to help us to follow trend lines where there is no outcrop. Magnetic anomalies are especially valuable to trace arcs and accretionary complexes because they have lots of iron-rich minerals in them, and this way you can distinguish them from the sedimentary basins. And here you see our data coverage. We couldn't find one single high-resolution database, so we used several papers to get the information. And also, we are open to any suggestion. If you know any database that can provide high-resolution data, please tell me. So when we simplified, we could plot the blue lines. At the end, we added our third layer, the distribution of magnetic rocks with known ages. We compiled almost 1,000 high-quality isotopic ages from the units that we discussed. And on this map, you can see a distribution from Mesoproterozoic to Silurian. In the next step, we drove this figure to compare Phanerozoic rifts and magnetic lineations to see whether they reflect younger events or not. And this figure shows magnetic lineations do not everywhere agree with the location or orientations of Mesozoic Cenozoic rifts. It indicates they mainly follow an older trend, possibly the Saharide trend. So by using our database, we started reviewing the lithology of units in order to understand their tectonic environments. Here you see a part of our 25-page table 1, only a short piece. It provides the important petrographic and stratigraphic information. We have defined several units by using this table, and at the end, we ended up with 9 first-order units. So this number can be more or less. It's probably more, but it's up to your interpretation, because we try to do our best with the limited surface exposure, especially in Sahara. While we are doing this, our fundamental assumption was the continuity both in time and space of major subduction zones. So we have to keep it in mind. After long discussions over Skype, we could identify the magnetic arc, accretionary complexes, four-arc basins, and even the ones invaded by arc magnetics. And we divided the Neoproterozoic into 3 stages: Tonian, Cryogenian, and Ediacaran. In this map, blue refers to Tonian, and these are the oldest units in the Saharides. There are also a few occasions of Archean and Proterozoic rocks, but they're mainly on the western margin of Ahaggar Massif. And here you see, this is the Ahaggar Massif, and you can see the old pieces in here, where it is the closest to the West African Craton. So purple refers to the Cryogenian, and pinkish colors show Ediacaran rocks. So there are also dark green colors in between. You can maybe see them in here. We will zoom in later. And they represent mafic rocks, mostly with unknown age, but surely they are Precambrian. This map shows an additional detail we expected to see: a younging direction of magmatic rocks dominated by northeast trend. It is almost visible in every unit. Let's zoom in to see the details better. So we will be zooming into the unit 3. And here we can see Tonian, Cryogenian, and Ediacaran units. And this is the younging direction. And you can also see this dark green colors. And from southwest to northeast, the yaks are getting younger. This is obvious. And the displacement within the units are clearly visible. And here you can see them. They are quite visible in here. And it is also pointed out by different researchers that these track slip faults, and we can also call them the Najd system in here, they are not products of a final collisions, but are products of the construction of the Saharides in Arabia and Egypt. So I will also show another figure from our paper. It's a frequency and probability distribution of isotopic ages from Saharides. And our histogram of isotopic age also confirms the activity of these faults in Tonian and Ediacaran. And here you can see them. This is the activity that can be seen from the isotopic ages. Unfortunately, we don't have any knowledge about cryogeny. It may be related with the poor exposure, but we are not quite sure. And our histogram also shows that continuous magmatic activity in Neoproterozoic, starting from the Tonian and even in the Stenian, but they are minor. And they show a peak in the Ediacaran, and then they diminish in Cambrian. So once we had our essential accidental units, here you can see them, the 9 units that we talk about, we took them and straightened them out and to put them in a row according to their strike-slip stacking order. And then we move them along this fold and tie them. And after we obtain a continuous arc, then we drew the magmatic fronts to see whether our assumption of a single arc is justified or not. And I can say we are mostly satisfied with the outcome. At the end, we extended our interpretation and reconstructed a single magmatic arc from the Ahaggar in the west to the Arabia in the east, and here we named it as the Tuareg arc. This is a dismember arc by arc slicing and arc shaving strike slip bolts while the subduction was going on. So all the units that we identified indicate that they contain subduction accretion complexes, and the source of the sedimentary components show an age range from Archean to the Cryogenian. And we realize this kind of age can best be found in the Congo Craton in south. So for the final reconstruction of the Saharides, we used a simplified Rodinia map from Lee et al. 2008. And we basically extracted the Congo and the West African cratons, here you can see. And we modified it to serve our reconstruction. I mean, we changed the paleolongitude, but we didn't change any paleolatitude because we gathered this data from the paleomagnetism. So as I said earlier, the age distribution of the pre-Saharid fragments in Tuareg arc point to the Congo Craton as a possible parent continent. So when the Tuareg arc is placed onto it, the length of the arc corresponds almost exactly to the total length of the eastern and northern margins of the Congo Craton. Here you can see it's like a necklace surrounding the Congo Craton. And this correlation is a good sign for our interpretation. And it seems that the Tuareg arc that was detached from the Congo Craton sometime before the Tonian, because the plutonic rocks associated with this arc magmatism are preserved on the Congo Craton as well. And near the end of the Cryogenian, the westernmost part of the arc collided with, here you can see, with the West African Craton. And this stage is also known as the Pharusian orogeny in the literature. And at the end of the ongoing approach between the Congo and the West African Cratons led to the internal deformation. Here you can see on the figure C. This deformation is done by the slicing and stacking of these units. And our final interpretation shows, with the exception of the Pharusian collision that I mentioned in here, there were no continental collision in the entire evolution of the Saharides until the final suturing in the latest Ediacaran or early Cambrian. So this also explains the great paucity of late Saharid age zircons in Phanerozoic deposits, because it was a debate, where were the Pan-African mountains? Were they really high enough to create any detrital zircons to the basins surrounding them? So here we see a distribution of detrital zircon ages in and around the Saharides. And we can say if there is no collision, of course, there are no eroded high mountain ranges, and you won't find these kind of age ranges in the basins. So the blue discontinuous lines separate areas in the south where the detrital influx diminishes with the evolving origin. Here you can see. And from the north, where there is a clear increase, it shows the mountainous land was or existed somewhere in the north, but not in the south. So the last touch is about the Saharan Lithosphere. So one of the anchor points of the Metacritone or Craton hypothesis was the presence of thick lithosphere beneath Sahara. This was a bit confusing because there are two sides claiming the opposite. One group, an example is shown from the Sob et al. 2020, support a thin, thick almost 200 kilometers thick lithosphere, whereas the others like Mackenzie and Prissy 2008 or Celia et al. 2020, they supported thin, average 70 to 80 kilometer thick lithosphere. So I should correct myself, because when I say thin, I mean it is thin compared to usual cratonic lithosphere, which is something between 200 to 350 kilometers. So as a former geophysicist, one hint about the tomography. So tomography results are strictly not data, but they are model predictions of mantle structure. In other words, they are interpretations. That's why they differ from each other in this level. So we all realized this judgment was beyond our skills, and that's why we consulted to an expert in my department here in Utrecht University, Wim Spakman, and he assured us by looking at the seismological evidence, a thick lithosphere, a cratonic lithosphere, is not present in Central East North Africa. And this was the end of the debate for us. So let's sum up. No thick lithosphere, no high topography, absence of collisional features, continuous alkalic magmatism, and too much strike-slip activity. None of these matches with the definition of a craton. And at the end, we can surely say Metacritone or craton is not a suitable name for this region. So my last words will be about the name, why we chose to use the Saharides. So one of the important reasons is there is no proper name covering all of these areas in the way that we described. And the closest one was given by Edward Seuss for the westernmost part of this north-south oriented orogenic belt. And we thought it would be appropriate to keep it that way and adopt this name for the entire orogenic system. So that was the end of my talk. I wish I could have or show some cool field photos. I don't have it, but since it wasn't a study based on a field, I cheated a little bit and found some photos from the internet. And here are a few photos from one of the Saharide massifs. It's the Jebel Uweinat. And this plate sits right across the borders of Egypt, Sudan, and Libya. And if you are familiar with the movie, The English Patient, you may also remember those paintings in the cave. And they are from the same region. So this is also famous with its prehistoric rock paintings. So if you ever go there, please do not forget to bring some rocks and take some good pictures for us. Thanks for listening and sparing your time for this talk.